Okay, good evening everyone. So we have been discussing on fields on DC machine. So first we have discussed the impact of only field winding, how the field looks like for if only field winding existed. Then we looked at the impact of slots which are necessary to house the conductors and the armature conductors. We understood how to get the flux density distribution step by step. First to get the mmf distribution, and then uh, to get a sense of how that will look like. And so let us now superimpose the two, and we'll look at the field distribution when um, both the field winding and armature winding are excited. So this is the case which we'll be starting with. So the field remains the same, armature also remains the same, only thing both are excited simultaneously. So field current of 1 ampere, number of turns per pole, that is one pole on top and one pole at the bottom, we have total two poles, and number of turns per pole is 500 as you can see here. So mmf per pole for this case is 500 ampere turns. And similarly for the armature we are looking the case for the armature mmf. So again armature mmf per pole can be calculated and found to be 405 ampere turns for the case we are looking at. But one thing we have seen that because the air gap path is quite low along the field winding axis. So the field the flux density due to field, that is quite strong compared to because of the very small air gap along its axis. On the other way, on the other for the other case, that is the armature winding, if you look at the axis for the armature winding, you can see that this axis sees the stator pole height, that is a significant number, as the air gap path, that is the minimum path length. So because of that, the strength of the magnetic flux density is quite low when compared with the field winding. The flux density strength due to the field winding excitation. So we'll get started. So first let us see what happens actually. So um, you can see that the flux line distribution, and on the right hand side you can see uh, the flux density magnitude plotted in color plot, where red indicates high flux density about 2 Tesla as you can see here, and deep blue indicates zero flux density, and in between they are spread and as shown with different colors. So what are the observations? You can see that let us start with the stator yoke. There is no noticeable change in these stator yokes in the flux density distribution, at least. And in the stator pole main body also, you can see in this portion, the main body, there is no noticeable change in the flux line distribution. It remains reasonably uniformly distributed. But you can see something interesting here, that one side of the stator pole shoe, that is this side, for this case that is the right hand side, gets uh, more crowded by flux lines, whereas here the number of flux lines are quite low. That is, you have low flux density in this stator pole as shown here, because blue colors, sky blue or blue colors are there. On the other side, other pole show, you have yellow or green colors, so that indicates that you have reasonably high flux density in this region. So if you compare with the flux density that you see in the stator pole main body, that is green, so green is probably here 1.2 Tesla, but if you see that it is going into yellow also, so yellow is higher compared to green, so you have higher flux density on one side of the stator pole shoe compared to what you even have in the main body or the stator yoke. So that is one observation that you can make. And actually you can see on the bottom side also, this bottom side left side gets um, uh, more dense with flux lines, whereas this right hand side that gets weaker with the flux lines. And in rotor what happens? So still you can see that the flux, if you actually try to plot the axis, what is seen, at least in this portion, obviously axis will get tilted as you go ahead. Axis is not straightforward in this case, because uh, at least in the stator, because flux lines are not uniformly distributed on the two sides, right? So in the yoke portion it reasonably remains vertical, but the main thing happens at the rotor. So in the rotor what is happening, you can see that the rotor flux axis has tilted like this. On one side you have some flux lines going like this, taking this path and then completing their path, and on other side, yeah, it again goes to the other side, but the axis, the rotor flux axis, that is tilted. That I think you can clearly see. I am again showing that tilted axis with by thickening that line. So this is the axis, this is the modified axis when of the rotor magnetic field when both are excited. And why is this happening so? Because if you look at the flux lines of produced by field and armature separately, then you will be able to get a sense of this. So now let us try to look at it. So for this case we were looking at dot here, cross here, and dot on the left side, cross on the right side. That is the condition we were looking at for the stator. So flux line direction will be upward, in the upward direction. So here flux lines will be upward like that, like this. On the other hand side, you will have again upward and radially inward flux lines due to field uh, uh, in these pole shoe regions. Now let us try to see what happens due to the excitation of the rotor. So if rotor is excited, let me indicate with black. So for the rotor, what was the direction that we took? We took dot in the uh, upper side conductors and cross on the bottom side conductors. That is the case for which we are the simulation is done. So the axis will be, so the flux lines direction will be right hand side horizontal like this. So as you have seen earlier, they will mostly flow through the stator pole shoe only. They will uh, flow somewhat like this. That is the of the path taken by the armature flux, right? So here you have all the cross conductors. So because it's cross conductors, it will be um, right hand side here, so it will be clockwise. So you have arrowhead direction like this and arrowhead direction like this, whereas in this side it is radially outward, it is radially inward here. So now if you look at what is happening in these pole shoe regions, now let us try to see. In this side of the pole shoe, on the right hand side top stator pole shoe, you can see that the stator flux, those are radially outward, and so are the armature flux. So they are aiding each other. That is why more flux, if both are excited, then more flux actually flows here, but what is happening on the other side? The stator flux lines are radially outward, but the rotor flux lines, the armature flux lines, they are radially inward. So they cancel each other, and that is why you have weakened or low number of flux lines on the left hand side. And same thing you can see on the left hand side of the bottom stator pole shoe. Here the armature flux lines are radially inward, and stator field flux lines, they are also radially inward. So both gets added up, and you have high flux density on the left hand side, and here the stator flux, they are radially inward, but the rotor flux, they are radially outward, so they get cancelled, and that is why you have weakened flux density on the right hand side of the bottom stator pole shoe. So that is what happens. One side of the pole shoe gets stronger due to the armature excitation, and the other side gets weakened due to the armature excitation. Effectively, if you see the field, okay, we'll come to that as I go ahead. So here is a zoomed in view of that. You can clearly see the axis of the rotor thing here. So this is the axis of that, and again you can see that for these cases, it is axis is not a straight line. It's not simple to define that, because you can see that even this flux line turns and goes around and then comes back, and so flux line, this particular flux line flows like this, which is on one side of the axis, and the next flux line just on the opposite side of the axis, this flux line, this flows also like this, and then it goes and then bends like that. So flux, if you have to describe the axis, it will be not a line anymore, um, but a curve, which will be um, flowing in between the two. So let us not complicate things with how with what we mean by axis for this case. But if side, that gives a fair understanding that the rotor axis, that is actually earlier it was vertical, but now it has tilted on the right hand side a bit. And why is the angle so low compared to the vertical angle? You can also explain it through, say, vector addition. So you have a very strong magnetic flux density vector due to field, say BF, flux density vector due to field, and you have a uh, quite weak flux density vector due to armature, and in space both these vectors actually get added up. So if you do vector addition, you get the resultant vector like this, because the BA magnitude is very very small compared to BF magnitude. That is why whatever this angle, say phi, this phi is quite close to 90 degree. So this also I think you can appreciate by looking at this picture. So now let us try to look at the in this changed condition, if we plot a air gap circle and move around and find the radial component and tangential component of flux density. So what happens? You can see that here again it is zero, reasonably zero. Some flux lines exist due to the armature excitation now, but the strength is quite low. That is why you have close to zero flux density here. But you have, so let us see the what were the values when only field was excited. So when only field was excited, then the value may be, so if this is 0, this may be 0.75. So I have to divide it into, so this is roughly say 0.37 0.37 Tesla, 0.4 Tesla, somewhere around that. That is the not 0.37. This is quite. This is, I think, if I divide it by 5 portions, this is zero point 0.4. So this is certainly higher than zero point 0.4. So 0.43, maybe 0.43 Tesla is the flux density peak, or this flat region flux density is about 0.43 Tesla, what we can see from this figure roughly. Now if I go back to the radial flux density picture, so 0.4 is this. So so earlier flux density was somewhere here. That was the flux density, radial component of flux density, when only stator was excited. Now you can see that this is actually the stator pole, one edge of the stator pole and another edge of the stator pole, and so this is the middle, 90 degrees the middle, 90 degrees the middle of the stator pole. You can see that on one side the flux densities get stronger, that is on the right hand side. In this case, that is for lower theta, it gets stronger, that is why the radial flux density that goes up higher. And the other side, that is the left hand side portion, because it gets demagnetized a bit or weakened a bit due to armature, so it gets lower compared to what was there for the stator. And same thing happens for the on the other diametrically opposite stator pole also. Here maybe the value, because before armature excitation was somewhere here for this region, that is some angle just lower than 270 degree, this portion it gets stronger, and on the other side there is some angle greater than 270 degree, it gets weaker. The field strength, the flux density magnitude gets weaker. Now let us try to see the tangential flux density distribution also, and in this case we'll take a zoomed in view and also try to have a better understanding of that. So you can see that there are many edges in the tangential flux density distribution. I have already discussed that wherever you have a teeth, and in between two teeth you have some slot. So this is one teeth, this is another teeth, and in between you have slot. So flux lines, if they are coming, if flux lines they were coming for a smooth rotor, now because of the presence of the slot, one side they will get bent like this on the left hand side, and on other side some flux lines will get bent on the right hand side. That is why if you look at the component of flux density, there will be so there are two opposite polarity components here. So one side it gets bent in the left hand side direction, that if I try to look at the circle, then actually it is along the direction of the arrow of the circle that I have indicated, that is it is positive, the value will be positive. On the other side, if flux lines bend on the right hand side direction, then that what if that flux direction is like this, then of course it has some radial component and also it has some tangential component. Now this tangential component is actually in the clockwise direction, so we have to the sign will be negative. On the other hand side, if the flux density near this other teeth is like this, then there is a strong radial component, and there is some tangential component also. So this tangential component with respect to the circle is actually in the anti-clockwise direction, so it is positive. So wherever you have any edge, or especially if you have slots, then at the slot opening, on the one side you expect some positive edge, and the other side you expect some negative edge. That is what you can see here. You can see that under the pole, that is from this portion to this portion, you have all these different edges. You can see that one positive spike and one negative spike, again positive spike, negative spike. That is the case you can look at. And when you are under only the that is, you are not looking at what happens in the slot opening, but you say you are trying to look at here, that is only the stator pole edge is there, then there is only uh, one there is no, one sign of the tangential component of flux density. It is either positive or negative. For example, here in this portion it is positive because flux lines tend to bend like this when entering the stator pole. So for this side, it is, if you take the tangential component of flux density, it is only in the anti-clockwise direction. That is why for this portion, that is right at the black line that I have indicated, just in vicinity of the stator pole shoe edge, you can see that the sign is only positive. There is no negative component here. uh, Similarly, you can look at here also. You can look at here, that is this portion. The flux lines, they tend to go like this, they tend to come out of this pole like this, and that is why if you actually take the two components, radial and tangential, there is a clockwise component of the tangential. That is why it is negative. And on the other side, if you look at here, on the other side of the pole, it is only positive. And why is the magnitude weaker? Because the flux density itself is weaker on the right hand side edge, on the bottom pole, whereas the flux density itself is quite strong on the left hand side. That is why whatever positive spike you are having, that is quite strong compared to whatever negative spike is there on the other side. So similar thing, you can look at the two edges of the stator top pole. The first one, that is the this edge, one edge, it is a stronger one and it is positive, and it is a weaker one on the other edge of the stator pole. So now I think you have good enough understanding of how tangential component of flux densities actually are, and whatever I discussed now, we will take a zoomed in view and try to visualize that. So what Yes. So what we are going to do now is we are going to zoom in this portion, whatever portion I show, using this blue dotted rectangle, whatever I try to show here, and this angle, this corresponding angles are actually shown here. This is between theta equal to 40 degree, theta equal to 40 degree to 60 degree, that is in between these two lines. This portion, in the air gap portion, we are going to see a zoomed in version of that. So this is a zoomed in picture. This line is theta equal to 40 degree, this line is theta equal to 60 degree, and in between we have one slot opening, that is we have this slot and some conductor here, and we have some opening here. The slot opening is at theta equal to 50 degree. Now the zoomed in picture for that spike of tangential component of flux density is actually shown on the left hand side in this picture, in this figure. So you can see that at 50 degree, if you see, the tangential component of flux density is actually 0, because on one side the flux lines bend on the left side, and on another side it bends on the right hand side. That is why no flux lines exist at the middle. So you have roughly 0 tangential component of flux density at the middle. Now what happens, I think if you take a closer look here, if you take a closer look at the flux lines, you will be able to see what I have discussed just now. You can see that the flux line, this flux line, it takes a bend and then flows like this. So this is how this flux line flows. So it bends, whatever its bending is on the right hand side, so that indicates some tangential component in the clockwise direction. So clockwise direction means B tangential has to be negative, so less than 0. On the other hand, on the other this say this uh, the next tooth, their flux lines go like this. So there is a bend on the left hand side. So if you take the components, you will see a tangential component. The tangential component will be in the counterclockwise direction. So that is why you see a positive thing there. So that is why greater than theta equal to 50 degree, that is if theta greater than 50 degree, that is this portion, there you see some negative tangential B tang value as shown here. So this is negative. On the other hand side, if theta is less than 40 less than 50, that is this portion, the tangential component is actually counterclockwise, so B tang is actually positive. That is why you have positive tangential component of flux density. Now you can also see that one is stronger and another is weaker. You can see that finally the right hand side gets magnetized, so it gets so this side, right hand side of this um, stator pole stator pole shoe, that gets that has higher flux density. So if you compare these two edges of these two rotor teeth, then you will see that whichever is on the right on far right compared to the other, that is having higher magnitude, and whichever is closer to the vertical line, that is having lower magnitude. You can see that this edge, you can see this edge, whatever I indicated here, this edge is actually closer to the or on the right hand side compared to the other edge. So this has more magnitude, this has the stronger B tang value compared to whatever you have on this edge, because this edge is more close to the vertical line. So this explains the relative values and the shape of tangential component of flux density, and you can see that it is roughly 0 when you are under rightly and directly under the teeth. If you are directly under the teeth, it is discharged. If it is directly under the teeth, then you have almost 0 tangential component of flux density here. So that is all. Now let us try to apply the the Maxwell stress tensor to get the radial force density and tangential force density distribution along the air gap. So we'll use these ones, and you know that this second component can be safely neglected while calculating that radial force, whereas for tangential force calculation both are necessary. So this is the radial force density distribution. So let us try to see what difference do we have from the case where only the field winding was excited? So if only field winding was excited, and yeah, mind you, this is the case for when there is no slots. So you have a reasonably high um, uh, and constant uh, radial force density under the pole, and it is almost constant at 0.1 Newton per mm square. Now if we look at the changed radial force distribution, so this is 0.1, this is roughly the 0.1 Newton per mm square what we had earlier. Now you can see that on one side, due to higher flux density or higher radial flux density, the radial force has also gone up, whereas on the other side it has gone down, and everywhere it is actually positive because the force everywhere it is radially outward. You can also understand it like this. So you have almost uniform strength north poles on the rotor, as shown in the as marked on the figure with this N, but you have a stronger south stator south pole here, and you have a weaker stator south pole on the left hand side. That is why the rotor north poles, they are almost equally strong, but a strong stator south pole that attracts the rotor on the right hand side more strongly. That is why you have higher radial component of force on the right hand side, and because the weaker stator south pole attracts the stator or rotor north pole with less force, that is why you have less radial force on the other side. That same thing holds here also. Here you have a very strong stator north pole and a very weak south stator south pole, but the rotor south poles are approximately of equal strength. So one side gets pulled with higher force, whereas the other side gets pulled by lower force. That explains why you have higher force uh, for one side of the stator pole and lower force on the other side of the stator pole. So that is about the radial force density. Now let us try to look at the tangential force density, where first time you will be able to see from the figure itself that if you actually compute the area under the curve, then you can see that positive notches are significantly higher compared to or higher compared to negative notches. So if I go back and see the notch tangential component force notches, so this was for the case where only the stator was excited, of course with no rotor slots. So you can see that the tangential force, the positive and negative things, they are symmetric, so they cancel them out. There is no net average tangential force, that is 0. And then if I go to the armature one also, you can see this is the tangential force density distribution when only the armature was excited. You can see that there are positive and negative notches, but visually you can see that they are cancelling each other, and if you actually take the average value, there will be no average value, only 0. So in this case also there is no net tangential force that can create some torque. So here, uh, so just to indicate, in order to create a torque you need a couple. So you need some, for the simplest case, you need some tangential force here and you need some tangential force on the diametrically opposite thing, and you can see that both these forces are actually in the counterclockwise direction. So So if I plot the force along the air gap, then for this case, for this very ideal case, you will have, say, whatever this is, if this is theta, then it will be theta pi plus theta. So this is theta, this is pi, and again this is theta, this is 2 pi. So if I plot, if I consider that the force density is force is only applied in this at this point, then I'll have that I'll have the tangential force versus theta, something like this. So if this is okay, there is some confusion, so this let us make it phi. So theta is this angle. So here we will have some positive thing, positive notch here, some tangential force, and 180 degree apart from that we will also have some positive notch only, because both are in the counterclockwise direction. So for torque production case, if I assume that the forces are acting on only these points, this point A and point B, this is point A, this is point B on the rotor periphery, then some positive force acts at point A and some positive force again acts on point B. Combination of these two forces causes the torque production. But you can see that for this case you have some positive notches here and some negative notches, or dominantly negative notches, and similarly some dominantly positive notches and some dominantly negative notches. So they cancel each other and you do not have any net torque. But if you actually look at the case where both these windings are excited, now you can see that positive notch is here. Also you have dominantly a positive notch, all over you have some dominant positive notches, here also you have dominantly positive notches. So you have torque, you have some net tangential net average tangential force that will cause some torque production also. But it is not like you have only two forces acting on two diametrically opposite points and they are producing the torque. Actually, if you look at, you will have multiple tangential force components acting on multiple points, and some in some places there can be some negative tangential force also, but you have multiple these forces, and similarly you will have multiple forces acting on the opposite side, and combination of these will produce the net torque that you want in a motor. Now if we try to realize the direction of the tangential force, from again the north and south poles that we have in this case, you can look at that you have almost two rotor north poles of almost equal strength, and you have a stronger south pole here and a weaker south pole here. So this north pole will attracted by the south pole in the radial direction, as well as in the some component will be in tangential direction, because this whole region is stator south pole and this region is rotor north pole. So there will be some force in this direction which will have some radial component and some tangential component as well. And on the other hand side, you can see that this south pole and north pole, because north pole is quite strong here, south pole is quite weak here, there will be some force, but that is quite weak compared to the force that we are having here. So I have not even indicated that. And for the diametrically opposite side, you have this south pole on the rotor, you have this north pole throughout this region here, again you have a weaker north pole on this side, and you have a south pole here. So the south pole the rotor south pole will get strongly attracted in this direction, which will have some radial component and some tangential component as well. So this force and this force will add up in the tangential direction, and they will lead to the torque production as we have. So net torque, some positive net torque is produced when both the field and armature windings are excited. So I'll take this opportunity to, okay, I'll probably discuss, okay. So this is how to, if you actually want to, if you have this kind of tangential force density plot, and now if you want to calculate what is the torque, what is going to be the torque acting on the motor, then this is the procedure. So tangential component force density as a function of the rotor or the circumferential position theta, that is, if that is known, then what is the net tangential force acting on the rotor. So let us take a small strip as shown here with blue color. This strip uh, makes some angle d theta at the center. So this arc length will be r into d theta if r is the radius, and if this is the axial length L, then this area as hatched by me, that will be r into d theta into L. So that is this infinitesimal area on the surface of the cylinder. Now some tangential force density gets applied on this area, so the net tangential force will be the surface integration of F tangential into dA, the surface integration over that. Now if you plug in the numbers that I have used in this case, that is L, the motor stack length is 80 mm and the rotor outer radius is 42.2 mm. So F tangential force will be, if you put this dA in this expression, L and R, they are constant, so they will come out. So L and R have come out. You have to integrate from 0 to 2 pi. You have F tang into d theta. So you know F tang as a function of d theta. So integration of that means what is the area under the curve. So you have F tangential something like this. Any question? Someone has unmuted, I think. Okay, so the integration means what is the area under this curve. Whatever is the area under the curve. So if you have positive and negative, then they will cancel each other. But if you have only positives and negligibly negative area, then they will add up. So you can numerically do this integration and find out the average tangential force, and torque is obtained by multiplying that by the radius r. So this is how you can calculate the torque, net average torque that you can have in this case. And for the approximated simplified expression that we come across readily in our textbooks, that is the torque, average electromagnetic torque, that is some K into flux per pole into armature current. So what is this K? K is this thing, number of poles into ZA, probably that is number of armature conductors, and you have 2 pi into A, where A is the number of parallel paths. So if I plug in the numbers, I think someone is unmuted. Let's check yourselves. So this is the expression. This is how to calculate K. So if you know all these numbers, you can calculate the K value for your machine. You can calculate the flux per pole. How to calculate the flux per pole? Again, you'll have to take a similar strip, and again in this case you have radial component of flux density as a function of theta known, that is this thing. You have the radial component of flux density and as a function of theta. Now this is one pole, this positive thing whatever you see, this is one pole, and this negative thing, that is the opposite pole. So now it tells you it is flux per pole, so you have to take the integration from 0 to pi, and if you do the same integration, flux per pole equal to surface integration of b rad into dA, and dA is L into R into d theta. If you plug in the numbers, you will get some number flux per pole 3.4 milliweber for this case. And armature current, if it is 30 ampere for which the simulation is done, you can calculate the average torque to be about 1.75 Newton meter. So it's on the same scale as we obtained in the other case, but it's an approximated one, and so there can be some mismatches due to, because it's an approximate expression. Now I will just briefly try to indicate that a common uh, uh, misnomer about how a DC, how a torque is produced in a DC machine. So generally, um, it's very easy, or it's very easy to explain in that way, that you have some field. So you have some field lines, and if you have some current carrying conductors, say dot due to its presence on this magnetic field. So the idea is the conductor, current carrying conductor, is seeing very high flux density, uh, uh, it's seeing very high flux density around it, and it is having some current flow through it. So because of this, you have to, what is this rule? You have probably some left hand rule. Um, Forgot which hand, left, or probably left hand rule only. So left hand rule will tell you that there will be some force acting on this conductor in some direction, say in this direction, right? So uh, so this is very commonly used um, for explaining how how torque is produced in a DC machine, but that is not actually physically true, because the idea is the conductor, the flux lines passes through the conductors, but if you actually look at a zoomed in view of the flux line distribution, if you take a zoomed in view of the flux line distribution, where is that? Yes, we were here. So the conductor is situated, um, in the slot which says no flux lines. So it is not physically true. The explanation may still hold, but it is not physically true that we can explain how torque is produced by in a DC machine. We cannot explain it through flux cutting of conductors. That holds for the case for galvanometers, like your moving coil ammeter or moving coil galvanometers, basically, where you have some coil through which current passes, and you have some strong magnet, and if some current flows through that coil, there is some force acting on, or torque acting on it, so it rotates by a certain angle, and that shows you how much current, that shows you a measure of the current flowing through that coil. So that is true, this explanation holds for um, the moving coil galvanometers, but not for machines where conductors are actually situated in the slots and no flux lines actually passes through the slots. So um, yeah, that may hold, but that is not physically true. That is the point. So actually there are the flux actually, or the torque actually gets produced due to these multiple tangential forces acting on these different edges of the teeth. So you can see, you can understand that on this edge, or use a different color, black is better here. So at this edge we will have some we will have some force, tangential force. Which way will it act? It will act probably in the it will act in the anti-clockwise direction, whereas on this edge, if you look at on this edge, it will be on the opposite side. For this edge, the tangential force will actually be on the opposite side, and again for this edge there will be some tangential force on this side, and this edge again there will be some tangential force on the opposite side. So there are multiple tangential forces acting on these different tooth edges, and the combination of them actually produces the torque that results in the rotation of the motor. So that's all I think for this in this lecture, that we have discussed what happens if the field winding and as well as the armature winding are excited, and how actually tangential forces are, and how uh, torque gets produced in any electrical machine. The same explanation holds, or the same type of observations can be seen in other machines also, like induction machine or synchronous machine. Whatever we have discussed in this series is only for those machines. We have only seen what happens for stator field separately and what happens for rotor field separately. If we superimpose them, we will see the similar case, that there will be some net tangential force when both are excited, and there will be some shift in the axis of the magnetic field to the rotors. Yeah, that's all. Let us stop for today. If not, we have any question. Is there any question? Okay. If not, then let us close. Good night.